Alright, we're going to do the first review video for Chapter 6. We're going to talk about electronic structures of atoms. So we're going to do our kind of review here about the nature of light. And the first thing we're going to talk about is light as a wave. Alright, so there are many different forms of radiation, and we call those electromagnetic radiation. So you've got your gamma rays, X-rays, UV, infrared, microwave, and radio. And we've got our wavelengths and our frequencies. Now you don't have to know the exact frequencies or wavelengths that go with these, but you do kind of want to know the order. Which ones have smaller, which ones are bigger, kind of like you have to know the order with the metric prefixes like kilo, hecto, milli, those kinds of things. So you do kind of want to know the basic order of which ones have small wavelengths and which ones have large wavelengths. They all do travel at the same speed. Remember that speed of light is c, and that's at 3 × 10 to the 8th, and that is in meters per second. Sometimes you will see it as 2.998, and that's the same thing as 3, obviously. All right, wavelengths are how long it is from peak to peak. That's that lambda. Okay, frequency is what we call the symbol is a nu, kind of like a V. All right, and that's cycles or the number of peaks that pass in a certain second. All right, so if I've got 20 peaks that pass, that's going to be 20 what we call hertz or seconds to the negative first. If you're dealing with the wavelength, that's going to be meters or nanometers. Remember that there are 1 × 10 to the 9th nanometers in a meter. And that's our equation that we used last year with the C equals wavelength times frequency, because again, all light travels at the same speed. Okay, section 2 talks about quantized energy and photons. We're going to deal with quantums and what quantums are. Okay, a quantum or quanta, all right, is a fixed amount, or it's the smallest amount or smallest quantity of energy that can be released or absorbed in a discrete chunk. So talking about a set amount. This is a quanta of energy, and then another quanta of energy, a very set packet. Okay, energy does come in packets. Think about it like stairs. If you walk up the stairs, you can't step in between stairs. So energy is the same way. You have to go this stair, then that one, then that one, then that one. So that energy is in a packet. Okay, we talk about a quanta. That's that QU here. I spent quanta. Okay, that quantum of energy is E, and it's E equals H times V. H is what we call Planck's constant. It's the guy who came up with this equation. And it's 6.626 times 10 to the negative 34th joules times a second. And then again, that's times our frequency, all right? And it needs to be, we're dealing with meters. And our energy then we're going to deal with, just like last chapter, is in joules, okay? Now, the photoelectric effect is what Einstein worked on. He worked on it after Planck, okay? And what he noticed was that light shining on a metal allows the metal to release its electrons, and that's why it kind of will shine off of a metal. So if you've got the light hitting the metal surface, it will then emit these electrons. And you kind of want to know a little bit about when these electrons get emitted. And so what he did was he took this energy or this light, bounced it off of a piece of metal. He noticed that these electrons then got pulled towards a positive terminal, and then a voltage source kind of pulled those electrons through, and we had a current reading. So we had electrons basically moving through the circuit. So when he set this up, he wasn't sure if he would get electrons moving or not, and he noticed that he had electrons moving through this circuit, and what he saw then was that electrons were actually being emitted, because there were current passing, and electron is basically, or current is basically electrons moving, okay? Each metal did have a frequency where no electrons were emitted. So he noticed that for this particular metal, at this spot, no electrons were emitted, but as soon as it hit this amount of frequency, I had electrons emitted. And so what he saw was this light behaving as a wave, or this stream of energy packets that we call the photon. So this photoelectric effect was the evidence that we had these things called photons, and then that our energy traveled in packets. So this E energy, this quantum, is actually the energy that our photons have. So, or the energy of a photon. So if you're dealing with a problem that's talking about the energy of a photon, you're dealing with the E equals H times V. And if a photon has enough energy to free the electron, it will. If it doesn't have enough energy, it won't. Either you have enough energy to walk up the step, or you don't. You can't go halfway in between 2 steps. Okay, the last little part we're going to look at here is line spectrum and the Bohr model. Okay, we did these last year. Most of this chapter we did last year. Okay, the spectrum of radiation is separated into different wavelengths. That's a spectrum, where we have this radiation that's separated. You can have a continuous spectrum that's actually all the colors, all right? And that's not any separation. but you have our line spectrum or emission spectrums. That's then when you contain only specific wavelengths. So a continuous spectrum is kind of all the colors, but maybe not the infrared or the UV, whereas a line spectrum is only specific wavelengths. And we get these when light is emitted, when electrons drop energy states, and remember, depending on what the gas is that we're looking at, you'll get these different lines. And remember back to last year, you had those glowing gases, okay? You had hydrogen or helium or whatever in a light source or in a voltage source, and it made the hydrogen kind of glow like a neon light glow. And when you look through the spectroscopes, you'll see these little lines. And those little lines are the light that's emitted when an energy drops from an excited state to a ground state and emits all that energy that it would have taken to go the opposite way, or to go from my ground state to my excited state. And that's what Bohr looked at. Okay, Bohr's model had electrons moving in circular paths. So we had this center nucleus, and we had all of these, orbits. Remember, a Bohr's model deals with orbits and electrons moving in very set paths. All right, and we have our ground state, which is the lowest possible energy state for that particular electron. So different electrons have different ground states. Okay, and the excited state is any energy state higher than the ground state for an electron. And there are all kinds of calculations you could do to figure out how much energy is lost when it moves from this state to that state. We don't really deal with the numbers as much as just how much general energy. So if I would drop from the 5th energy state to the 1st, that would be more energy than if I would drop from the 2nd to the 1st. And that's pretty much the end of review video 1.